Okay, hello everyone. Okay, we were considering the subspaces. So first of all, we considered a vector space. Vector space is a set with two operations. One is the addition of arbitrary elements, and the other is the scalar multiplication. So uh, this set is closed under these two operations. So that means when you add any two elements, the result is some element within the set. And when you multiply any number, which is called a scalar, to an element, the this product is well defined, meaning the result is included in the given set. And in addition, this addition of two arbitrary elements or scalar multiplication satisfy several properties, right? So, I mean, for example, the addition is commutative, associative, and there is a zero vector, and there is some vector which make, I mean, given any vector x, you can find y such that their sum becomes a zero vector. And if we multiply a number one, then the vector is not changed, and so on, right? So we have those properties, requirements for a set to be a vector space, right? Now, once you have a vector space, sometimes we are interested in a subset of this vector space, and if this subset happens to be a vector space, then we call that subset as a subspace. Now, given a set V, sometimes I mean, and if I know that this V is a vector space, and if I consider some subset, and if if you can show that this subset satisfies these two properties in the slide, these two requirements, then the set will be a vector space. In other words, that subset will be a subspace. Now, what are those two? We just need to show that this subset is closed under the addition and scalar multiplication. So if those two are satisfied, then the set will satisfy all the other requirements for a vector space. Okay, and we want to consider some examples. So given m by n, so previously we considered the set of, say, m by n matrices, of course, say real matrices, I mean the matrices with real entries. If I call this guy as a V, then this V will be a vector space, and we could show that this V satisfy all the requirements. Now, given this set V as a vector space, okay, so suppose that I know that this V is a vector space. Now, I mean, and okay, so given, so this is what we considered the other day. So let me raise it a little bit. Okay, so I know that, say, the set of n by m matrices is a vector space. Then it's a subset, say, the n by n symmetric matrices will be a subspace because the set is closed under addition and scalar multiplication. So that's what you can easily conform. So, oops, sorry with that. So the set, this is the set of symmetric matrices, n by n symmetric matrices will define a subspace. And we also consider this. And Another example of those matrices will be the following. Suppose that, so I have a matrix, some m by m matrix, and we say the matrix is an upper triangular matrix if all the entries below the diagonal entries are zero. So what are the diagonal entries? The entries with the same row and column number, say A sub 1 1, A sub 2 2, A sub 3 3. These are diagonal entries. So given a matrix, if the entries below that numbers are all zero, then we say the matrix is an upper triangular matrix. So from something like this, A, this 1, 5, 8 are diagonal entries. And if you look at the entries below those numbers, you have only zero, right? So this A will be called a upper triangular matrix. In a similar way, if you have just a zero above the main diagonal entries, then that matrix is called a lower triangular matrix. Okay, so we say the matrix is a lower triangular matrix if the entries above the diagonal entries are zeros. So in case of the upper triangular matrix, the entries below the diagonal entries. So A sub ij is zero whenever I is greater than j. And the matrix will be lower triangular if the A sub ij is zero whenever I is less than j. Okay. So in case of the upper triangular matrix, the diagonal entries or entries above the diagonal entries do not matter. Okay, they can be zero, they can be non-zero, it doesn't matter. Okay, as long as the entries below the diagonal entries are zero, then that matrix is an upper triangular matrix. In a similar way, if the entries above the diagonal entries are zero, then the matrix will be a lower triangular matrix. Now, if your matrix is a square matrix, and if that matrix is upper triangular and lower triangular, in other words, if the entries above the diagonal and below the diagonal are all zeros, then such matrix is called a diagonal matrix. So B has zeros below the diagonal and above the diagonal. So B is a diagonal matrix. And diagonal entries may be zero. So as an example, if I consider, say, 3 0 0 0 minus 2 0, and then if I have just 0 0 0, this is another diagonal matrix. And D with 0 0 0 0 0 0 0 0 0 is also a diagonal matrix. Okay, so this B, C, D are all diagonal matrices. Okay? And B, so here B, C, D are all diagonal matrix. I can say A, B, C, D are all upper triangular matrix. Okay. And you can say B, C, D are also lower triangular matrices. And suppose that if I consider the set of diagonal matrices, it will be a subspace of the n by n square matrices. It is a trivial, right? Oh, one more thing. We say A is a, a on a unit upper triangular matrix if A is upper triangular and diagonal entries are all ones. And we say A is a unit lower triangular matrix if A is lower triangular and diagonal entries are all ones. In that case, we say A is on lower triangular matrix. Now, if I just consider the n by n upper triangular matrices, it will be a subspace of this n by n matrices. But if I consider n by n unit upper triangular matrices, it is not a subspace, right? So you can easily check this. Given a square matrix, given some n by n matrix, the trace implies the sum of the diagonal entries. So it represents the value representing the sum of the diagonal entries. In other words, given this n by n matrix, you can find first row, first column entry, second row, second column entry, up to nth row, nth column entry. And then if you add them, you get certain value, and that value is called the trace. Now, suppose that and if I consider the collection of n by m matrices, so if I consider the set of n by m matrices having zero trace, the trace equal to zero. If I consider such a matrix, so if I choose any two elements, and if I call this subset by V, so if I choose any two matrices from V, then that implies the trace of A and trace of B are all zeros. Now, what is the trace of A? So, okay, let me rewrite this. So, trace of A is A sub 1, 1, A sub 2, 2, up to A sub n. This value is 0. And trace of B, which is B sub 1, 1, B sub 2, 2, up to B sub n is 0. Then what is the trace of A plus B? Then the trace is the sum of the diagonal entries. What are the diagonal entries of A plus B? Oops, sorry about that. So that is the first row, first column entry of this, and second row, second column entry of this, up to nth row, nth column entry of this. And we know that that is the same as and that will be if I just consider the sum of A11 up to ANN and consider the remaining numbers. Since we selected A and B from V, the traces of A and B are all zeros, so the result will be 0. So that means A plus B will be a matrix in V space because its trace is 0. Then how about the trace of C times A, where C is any arbitrary number? Then that will be, and this is C times A11 up to ANN, and the expression inside the parenthesis is 0, and this is 0. So that means C times A is also in V space. So that means this space, this set is closed under the addition and scalar multiplication, which means this is a subspace of n by n matrices. But note, if I consider the set of n by n matrices having trace equal to any non-zero value, say 1, is not a subspace, right? For instance, the set 0 vector 0 matrix is not included because in case of the 0 matrix, the trace is 0, right? So only when you consider the set of matrices having the trace 0, that set will be a subspace. But if the trace, if you consider different value, the set is not a subspace. The set of matrices in m by m, the set of m by m matrices having non-negative entries is not a subspace of, right? Because it is not closed under scalar multiplication. I mean, some similar example is this. We know that R2 is a subspace, right? But if I consider the points in the first quadrant, is not a vector space, is not a subspace. Now, given some vector space, if I have, say, C1, C2, if C1 is a subspace and if C2 is a subspace, then there will be some intersection W. Okay, so this W denotes the intersection of two or several subspaces. Then this W will be a subspace whenever C1, C2, or these C are all subspaces. Because if you choose any two elements from W, then say X and Y, if X and Y are chosen from W, then that means X and Y are in the intersection of C1 and C2. That means X and Y are contained in C1 as well as C2. So X and Y are in C1 and they are also in C2. Since these two are vectors in some subspace, we know that C1 is a subspace, then X plus Y is in C1. And since X and Y are also vectors in C2, X plus Y will be included in C2 as well. So that means X plus Y will be included in the intersection of C1 and C2. Right? And also, if I multiply any number to X, then it is also in C1 and it is also in C2. So C times X must be included in the intersection of C1 and C2. So that means this intersection is closed under the addition and scalar multiplication. And well, I just considered the case when you have only two subspaces, C1 and C2, but if you have multiple, if you have several such subspaces, we can extend this, right? So, so, or this intersection of a subspace is a subspace. Then the next question will be then the union. How about, so suppose that I know that this V is a vector space and say W1 and W2 are some subspaces of V, then does that imply that the union of W1 and W2 are subspace of V? Let us consider the case when V is R2 space and say W1 is a collection of a multiple of say 1, 2 vector. So C1 is an arbitrary number. So this is a subspace of V, R2 space. W2 is say collection of say 2, 0. Okay. Then when I consider the union, okay, so definitely 1, 2 is a vector in W1 and 2, 0 is a vector in W2. So if I take the union, so this is included, so is in the union of, is it in the union of this? So if I choose 1, 2 vector and 2, 0 vector, if I add them, it is a 3, 2 vector. Is it in the union of W1 and W2? If if it is in the union, this 3, 2 must be in W1 or W2 or both, right? So is a 3, 2 vector in W1 vector? Or in other words, is 3, 2 a multiple of 1, 2 vector? No, it is not a multiple of 1, 2 vector. Then is the 3, 2 a vector in W2? Or in other words, is the 3, 2 a multiple of 2, 0 vector? No. So when you choose one vector from W1, one vector from W2, okay? But their sum is not in the union. So their sum is not included in the union of these two sets. So the union of W1 and W2 may not be a subspace of V in general. And the example is given in blue. Then, okay, so the intersection of two subspaces will give you a new subspace. But union does not give you a subspace in general. Okay? So, as I said, the intersection of subspaces is a subspace. We could prove it, but the union of subspaces is not in general a subspace. So we want to consider something slightly different. So we want to consider something called the summation. So given two non-empty subsets, we want to consider something called the sum of these two sets, which is denoted by this. Okay. So that is the collection of all the elements which can be written in the sum of x and y for some x in S1 and some y in S2. Now, given this summation, given this sum, we say some vector space is the direct sum of W1 and W2 if, first of all, W1 and W2 are subspaces of V, and secondly, the only intersection between W1 and W2 is the zero vector. Okay? And third, their sum is V. Okay? So W1 and W2 are assumed to be the subspaces of V. The only intersection between W1 and W2 is a zero vector, and their sum is V, not the union, okay? Then, and in that case, in case of the direct sum, we put this plus sign inside the circle. So if you see this notation, then that implies the direct sum. Here is an exercise problem. You can easily show that if V is, so given this V, given a vector space of V, when I consider the sum, okay, if I consider the sum of two, then that will be a subspace. You can prove that. So you can consider my previous example, the W1, what was the W1? There's a multiple of 1, 2, right? So multiple of 1, 2. And W2 is multiple of 2, 0. You can consider the sum of these two spaces, and you can show that their sum is a subspace. And okay, so you can check. And I need, okay, and if you look at the exercise, there is a more problem regarding the sum and the direct sum, and I need the definition of direct sum later. But so that's why I'm introducing this definition here. But anyway, the point here is the sum of two subspaces. If you consider the sum of two subspaces, then their sum will define a new subspace. And okay, let's go to the next section. Suppose that V is a vector space and S is a some subset, non-empty subset. We say V, some vector V is a linear combination of vectors in S if vectors if there exists some numbers, some vectors u1 up to un in S and some numbers a1 up to an such that this V can be written in this form. So if V can be generated as the sum of A1 U1 A2 U2 up to AN UN. In that case, we say V is a linear combination of U1 up to UN, and A1 up to AN are called the coefficients of the linear combination, or sometimes they are called the weights of the linear combination. And and in any vector space V, 0 times V will be the 0 times V will be the zero vector. So the zero vector is a linear combination of any non-empty subset of V. Okay? So as an example, say 1, 2, 3, 4 can be written as 1, 0, 0, 0 plus 2 times 0, 1, 0, 0 plus 3 times 0, 0, 1, 0 plus 4 times 0, 0, 0, 1. So this 1, 2, 3, 4 is a linear combination of these four matrices. Or you can say it is the sum of 1004 plus 0100 times 2 plus 3 times 0010. So I can say the matrix is the linear combination of these three matrices. Okay. If I consider, say, second order polynomial, say x squared minus 3x plus 2, it can be written as x squared plus minus 3 times x plus 2 times 1. And at this point, this 1 is the constant of function 1. You know what I mean? So the function having this graph, okay? So this is the constant of function 1. And function x will generate the graph of this, and x squared will generate this graph. So given these three functions, the x squared function, x function, and the constant function 1, x squared minus 3x plus 2 can be written as a linear combination of x squared, x, and 1 function. Or I can say x squared plus 1 times 1 plus minus 3 times x plus 1 times 1. So I can say the same polynomial can be a linear combination of x squared plus 1, x, and 1 function. Okay? So at that point, The weights are 1 minus the 3 and 1. So one vector can be written in various forms. Okay. Now, let us consider the following example. This is very interesting, and quite intuitive. I mean, informative. So let us look at this example. So we want to determine if some vector, say 2, 6, 8, can be written, okay, as a linear combination of 5 vectors, u1, u2, u3, u4, and u5. u1 consists of 1 to 1, u2 consists of -2, -4, -2, and so on. u3, here are u4 and u5. So given these 5 vectors, I want to determine, okay, I want to determine if this given vector 2, 6, 8 is a linear combination of these 5 vectors. So if this 2, 6, 8 vector is a linear combination of these 5 vectors, then there should be some coefficients, right? There should be some coefficients such that the given 2, 6, 8 vector is a linear combination of u1 up to u5 with a1 up to a5 as the coefficients or as the weights. Now, a1 u1 is this. Now, how do I define this expression? This is a scalar multiplication between a number a1 and a vector 1 to 1. So that is interpreted by a1 to a1 and a1. The second vector a2u2 is representing this, and this scalar multiple is interpreted by -2a2, -4a2, and -2a2. And the third one, a3u3, is this, and that implies a3 times 0, which is 0, and then 2a3 and 3a3. Then we need to consider a4u4, which is a4 times 2, 0, -3 vector, which will give you 2a4 and 0 and -3a4. Then the fifth vector is this, which produces -3a5, 8a5, and 16a5. Now I have the sum of 5 vectors. Now, how do I add these 5 vectors? You need to add corresponding entries, which means given these 5 vectors, you first consider the sum of first entries. That will give you this one. Then we consider the sum of second entries, which produces this. Then we consider the third component of these vectors, which produces this one. Okay? So this is what we get by considering the linear combination of u1 up to u5 vectors. Now we want to determine, okay, if there are 5 numbers such that this vector equals 2, 6, 8 vector, then what does this equality imply? Equality between this 2, 6, 8 vector and this vector implies that the corresponding numbers are the same. So then, oh, sorry, not this one, sorry. So the corresponding entries. So the first entry equals 2, second entry equals 6, and the third entry equals 8. So the equality between two vectors imply these three identities. So the first entry equals 2, second expression equals 6, and the third equals 8. Okay, so that's what the equality between two vectors imply, right? Now, given this equation, we want to check whether such some a1 up to a5 satisfying these five equations exist, right? So to solve this system, we want to replace it by by another system with the same solution set, but which is easier to solve. When I say easier, that means the systems have many zeros. So I want to introduce many zeros into the system, but I want to keep the same solution. Okay, so the idea is this. Okay, given this system, three equations. Okay, here is my first unknown, a1. Okay, a1 is my first unknown. Now, I want to have a1 only in the first equation, and I want to eliminate a1 from the second and third equations. How can I do this? Okay, in the second equation, I have 2a1. If I multiply negative 2 to the first equation, what do you get? If I multiply negative 2 to the first equation, then you get negative 2a1 plus 4a2 plus 0 minus 4a4 plus 6a5 equals to negative 4. What if I add this equation with this newly obtained equation? If I add these two, the first term of the first equation is 2a1, while the first term of the second equation is negative 2a1. If you add them, you get 0. And if you add the remaining terms, actually negative 4a2 plus 4a2 will also give you 0. Then this 2a3 minus 4a4, I'm sorry, 2a3 plus 0. So there's no term here in the second equation. So the third equation is 0. So 2a3, and then the next term here is 0 plus minus 4a4 will be minus 4a4. And then the fifth term is 8a5 in the first equation, and the corresponding term is 6a5. If you add them, you get 14a5. That equals 6 plus minus 4, which is 2. So this is the equation I obtained by adding these two. So if I replace the second equation of the original problem with this newly obtained equation, the solution won't be changed, right? But I have somewhat simpler equation because I have more zeros. In a similar way, given this first equation, I have a1, and I do not want to have a1 in the third equation. So that means I want to eliminate this a1. So how can I eliminate this negative 1 and this a1? I need to add negative a1. So I want to multiply negative 1 to the first equation. If I multiply negative 1 to the first equation, you get negative a1 plus 2a2 plus 0 minus 2a4 plus 3a5 equals to negative 2. If you add these two equations, you get this one. So the three equations in the system 1 will have the same solutions as the three equations in system 2. Okay? Now, by eliminating A1 from the second and third equation, I could also eliminate A2 in the second and third equation. Now that's fine, it doesn't matter. Now, when I look at the system 2, okay, I have three unknowns. I mean, in the second equation, I have three unknowns, A3, A4, and A5. So what I want is I want to keep this A3 only in the second equation, but I do not want to have A3 in the third equation. So I want to eliminate this 3A3 from the third one. But before I do this, if you look at the coefficients of the second equation, I have 2, -4, 14, and 2. They are all even numbers. In other words, they are all multiples of 2. Okay, so I can probably simplify this equation by dividing the equation by 2. So if I do that, the coefficients become smaller. Now, given this, if I multiply -3 to the second equation and then if I multiply -3 to the second equation, you get -3A3 plus 6A4 minus 21A5 equals to -3. And if you add these two equations, you can erase A3 from the third one, and this is what you get. Okay, now given this equation, okay, I have A4 in the third equation. Now A4 also exists in the first and second equations, and I'm not happy with this too. In the first and second equation, I want to erase 2A4 and -2A4 from the second and third equation. Now, you can guess now how I can erase those two numbers from the first and second equation. You multiply some number to the third equation, and then probably you will add that to the second and the first equation. So in order to eliminate this 2A4 in the first equation, probably you want to multiply -4 to the third equation. If you add if you multiply -4 to the third equation, you get sorry, not -4, but -2, -2. Then you get -2 times A4 and plus 4A5 equals to -6. And if you add these two, then 2A4 in the first equation will be erased. Right? Of course, the coefficient of A5 and the value on the right hand side will be slightly modified, but that is fine because I can eliminate this A4. And in a similar way, I could eliminate A4 in the second equation. Then you get these three equations in system 4. Now, it is easy to solve for the it is easy to solve for the A1 in terms of the others. And in the second equation, I could solve this for A3 in terms of A5. And I can solve the third equation for A4 in terms of A5. So A1 can be found by this. A3 and A4 can be found in a similar way. So we could find some solution, right? Given this system, okay? So if you choose any values for A2 and A5, so if you choose any values for A2 and A5, then depending on those values, the values of A1, A3, and A4 can be derived. Okay, okay, so I have just one. question. So, how can this operation happen with preserving of solution in the system? Now, actually, that's what we learn in elementary school days. So, so let me review those. And so suppose that I have equation 1, equation 2, equation 3. And so as an example, so I have, say, x plus, say, suppose that I have two equations for simplicity. Say x plus y equals to, say, 5, and x minus y equals to, say 3, something like this. And then given this two system of two equations, one operation. So if I have this system, if let me call this guy as system 1. Now, how about the system of equation 2 and equation 1? So if I define the system with x minus y equals to 3 and x plus y equals to 5. So if I mix the order of the equations within the system, we know that the solution is not changed, right? So in other words, if I consider any interchange of any equations within the system, it doesn't change the solution, right? So system 1 and system 2 will have the same solution. Now, what if I multiply some number to some equation, say, keeping the equation 1 as it is, but in case of equation 2, what if I replace the equation 2 with some number times equation 2? Say, x plus y is the same, unchanged, but in case of the second equation, what if I multiply negative 1 to the second equation? Then this equation will become negative x plus y will be negative 3. So if I consider this problem, the solution won't be changed, right? Of course, if you multiply 0, then you have a problem. So you don't want to multiply 0, right? Because if you multiply 0, then you lose all the information. So unless you multiply 0, if you can multiply any number, any non-zero value, then the solution will be the same. Now, the third operation is important. Given this equation 1 and equation 2, if I replace any equation with equation 2 plus some number multiple of equation 1. So, for example, if I multiply negative 1 to the second equation, you get negative x plus y equals to negative 3. If you add this to the first equation, okay, so I'm multiplying some number to some equation. So let me consider this. Let me change this. 1, 1, 2. Okay, so given this equation 2, you multiply any number and then add it to another equation. Say, so negative x plus y equals to negative 3. So if I add this x plus y equals to 5, if you add them, you get 2y equals to 2. So if I replace the first equation with this new equation and the original second equation, the solution won't be changed. So that's what we practiced in the high school algebra class, right? So if I use this, then the solution is not changed, right? So I'm just repeating these operations. So given this, let me go back to the beginning. So I want to solve this system 1, and what I want is I was just repeated the third operation that is called replacement. So given this is important. So given row, say it's not row, but the given equation I, and given this equation I, you multiply some number to this equation I, and then add it to, say, equation J, and if that overrides the existing equation J, so if this overrides the equation J, so this is my new the Jth equation, and here is my old one. Then if I define my new Jth equation by this, then that operation will be called replacement, and that won't change the solution, right? So I'm just repeated this operation. Given the system 1, what I did was equation 1 times negative 2 plus equation 2 will override the equation 2. And equation 1 times negative 1 plus equation 3 will override equation 3. That's what I did in system 1. Okay? So if I do that, you get system 2. It's actually system. Once I have this, I'm just multiplying. At this point, since I have just the multiples of 2 in the coefficients of the second equation, I just simply divided all the coefficients by 2 to get these smaller coefficients. And then using this second equation, I multiplied my third equation is the equation 2 times negative 3 plus the old equation 3. That's my new third equation. So and then I performed similar operations, okay, to eliminate a 4 in the first and second equation. So that's what I did. Okay. Then you get this system 4. Now what you can do, what you can observe is that so this a1 appears only in the first equation, and a3 appears only in the second equation, and a4 appears in only in the third equation, and a1, a3, a4 can be expressed in terms of a2 or a5 like this. So with this expression, if I give you any value for A2 and A5, I can find A1, A3, and A4. So for example, if I plug in 0 for A2 and A5, then A1 will be negative 4, 7, and 3. If you change the value of A2, you get different value for A1, right? So the point is, my 5 coefficients can be expressed in terms of A2 and A5. And the point is, when you assign any values for A2 and A5, we could find all 5 values from A1 up to A5. That means such 5 weights, such 5 coefficients will exist. In other words, 268 is a linear combination of these 5 vectors. Okay, so So 268 is a linear combination of these five vectors. Now, before I go to the next slide, now to answer this question, to answer this question, how did I solve this? Let me go back to this slide. So if I consider this a 268 vector, and if I give you these five u1 up to u5 vectors, and to answer the question, right? So the question was to determine if this 268 vector can be expressed as a linear combination of five vectors from u1 up to u5. Now, by using the definitions of vector addition and scalar multiples, we could derive an equivalent system of equations, this equation 1. So sometimes instead of asking the same question, I may ask you to solve this system of equations. Okay? And then in that case, you need to determine if u1 up to u5 exist, satisfying this is system 1. Okay, so we have two different expressions in math. Okay, I may ask you to determine one vector can be expressed as a linear combination of some other vectors, or for the same question, I may give you a system of linear equations, and then I can just ask you to solve the given system. The procedure will be the same. Okay? So from the system of equations, I could simplify somehow, right? I just eliminated some unknowns. Now, so the procedure just illustrated, and as I said, and actually this slide just explains that you can interchange any two equations within the system of equations, or you can multiply any non-zero value to some equation, or you can perform some replacement operation in this sense. Okay, and those three operations will not change the solution. And by using the combination of these operations, I want to simplify the given system of equations. So we want to consider three operations: interchange the order of any two equations within the system, or I can multiply the equation by any non-zero value. You can add a constant multiple of any equation to another equation. So that means, so here another means, so the replacement is, as I said, is this: the equation I times a constant can be added to another equation. So that plus equation J will overwrite the equation J. So that is my, as I said, a new jth equation, and here was my old jth equation. And so here another means I and J cannot be the same. Okay? Because, you know, if C is negative 1 and I and J are the same, then you have a problem because the jth equation will be replaced by 0, right? So you don't want to perform such a replacement. So we always consider, when you consider the replacement, I and j must be different. So this is interchange. I will call the first operation by interchange operation, and the second one will be called scaling. The third one will be called replacement. And I will, and these are called elementary row operations. Okay. And we will use these three row operations quite often. This is the only weapon you have in when you solve the system of equations. So please remember these three row operations. They are very important and useful. Okay. Now, before I go to the next part, one very important observation you have to make is that those operations are reversible. In other words, we can undo those operations. Meaning, for example, suppose that I have x plus y equals to 5 and x minus 5 equals to 3. And then if I perform the interchange operation, then you get x minus 5 equals to 3 and x plus 5, y equals to 5. Then if I interchange these two equations one more time, you go back to the original system. So I can undo this interchange operation. Right? Now, how about scaling? Say if I multiply 3 to the first equation, you get 3x plus 3y equals to 15 and x minus y equals to 3. How can I undo this? You can divide the first equation by 3. Or, so if you perform the multiplication by 3, then given this first equation, you can just multiply 1/3 to the first equation, then you obtain the original problem. And since you are multiplying a non-zero value, you can always find this reciprocal of the multiplying scaling factor, right? And how about the replacement? What if the equation 2 is replaced by the negative 1 times equation 1 plus equation 2? If that overwrites the equation 2, then the first equation is not changed. But if I multiply negative 1 to the first equation, you get negative x, negative y equals to negative 5, and x minus y equals to 3. So if you add them, you get negative 2y equals to negative 2. So if that overwrites the second equation, you get negative 2y equals to negative 2. So this is my new system obtained from the replacement. Now, how can I undo this operation? How can I go back to the original problem? You can replace the second equation by, instead of multiplying negative 1, you can just multiply just plus 1 to the equation 1 and then add it to the current second equation. Then if you add these two equations, you get x minus y equals to 3. So you can go back to the original situation, original problem. So these operations, these three operations can be used to simplify the given systems. So it can be used, they can be used to simplify the given system of equations. But one of the important properties is that they are all reversible. Okay? So I can undo the interchange operation by performing the interchange one more time. I can undo the scaling by multiplying the reciprocal of the scaling factor. And if you multiply c to the equation I and then add it to the equation j to get the new equation, then instead of adding that c multiple of equation I, you can subtract it from, right? You can subtract it from the equation j, then the previous jth equation is obtained. So these three operations are quite useful, quite simple, okay? And we are going to use them only these three. And one of the nice properties is that these operations are all reversible. Okay? So please remember this. So in chapter 3, we will prove that these operations do not change the set of solutions. We will confirm that one more time, even though you studied this in high school days. But okay, and when we look at this final form of the system of equations, we have the following pattern. First, the first non-zero coefficient in each equation. So I have a1, a3, and a4. Those are first non-zero the non-zero elements, non-zero terms, right? Now the coefficients of those terms are all ones. So a1, a3, a4 are multiplied by just ones. Okay, so the first non-zero coefficient in each equation is 1. And if some unknown is the first unknown with a non-zero coefficient in some equation, okay, so say if a1 is the first unknown with non-zero coefficient in the first equation, then this a1, this unknown, okay, occurs with a zero coefficient. That unknown does not appear in the other equations. So the unknowns occur with a zero coefficient in each of the other equations. Then that means that unknown does not occur in the other equations, right? So a1 appears only in the first equation. A3 appears only in the second equation, and then A4 appears only in the third equation. Now the third one is a little bit confusing, so probably please read this, okay? And then let me explain this on the day after tomorrow, okay? So this is a little bit confusing, so please read this, okay? And let's call it a day, and okay, see you next time. If you have any questions, please email me.